We want to take our circular motion a little bit further now and look at what happens when we put it inside what we call a conical pendulum. So what we want to do here is basically we've got a bob that moves around, and it moves around in a conical pendulum. So it moves around in a circle, but it might be attached to a string or a rod or something like that. So we want to look at what the forces are that are being performed on it, and then derive some results such that the tan of an angle there that it's forming is equal to v squared on a times g, and h is equal to g on omega squared. Also, we want to look at what happens to the pendulum as the features vary. So as we start to change the velocity or the angular velocity or anything like that, what happens to the pendulum there, and then start solving problems involved there. So what it requires is to understand what's happening. So we've got a mass that's sitting on a circle, and it's at the end of something like might be a light fixed string, and we say it's light, so that doesn't add anything to the weight of it. Or it might be a fixed rod and it moves smoothly, so there's no friction that's going to occur there. So what happens is we want to start to get a few things we want to start to get a few equations happening from this. So we've got it moving at a constant angular velocity. So the theta to t is constant. So from this we've got it moves in a radius, so it moves around in a circle there at the end of that string or rod or whatever it's going to be. Then we've got a length of the string there. We've got a height that it's going to be above the center of that circle there. We've also got tension that's going to, forces are acting upon there. There's tension in the string, and also there's going to be the mass times the gravity. It's going to be wanting to be pulled down. Gravity's going to try and pull it there. So the two tensions that are, the two forces that are acting are the tension there and the gravity acting there. So what can we establish? Well, we know if that's theta there, then we can get r is equal to L sine theta. We can also get h is equal to L cos theta. We can start to establish that because cos theta would be h on L, and so h can be L cos theta. So that's if we look at it in terms of the distances there. We can also start to look in terms of the forces that are starting to occur. So we can get forces that are existing in there with the r and h as well. So r would be equal to the tension times sine theta, and h is equal to tension times sine theta. So instead of using L, we're using the idea that we've got a tension occurring there. We usually want to solve our forces vertically and horizontally because that's what we know we've got going on. So if we look at this diagram here, that we've written h here, but really if we take this side and put it over t, that would be equal to cos theta. So this side's really equal to t cos theta. And that's opposing the mass times gravity. So those two forces must be equal. So tension times cos theta would be equal to mass times gravity because Newton's third law, that they have an opposite and equal reaction. So that's what happens vertically. Horizontally, we know that we've got t sine theta from this diagram here. Like that's t there, and that's theta. Then instead of r, this could be written as t sine theta. So that's where we get the idea along the inside towards the center. From the particle at all times, we're going to have t sine theta acting towards the center, and we've got the m omega squared r, which is the normal force that's acting against it. So t sine theta would be equal to m omega squared r. So that we've solved that horizontally. So there's our two situations. Vertically what we've got, and horizontally what we've got there. So we call them equations 1 and 2, and then we can start getting other equations here. We know the strings can't be horizontal because the angle's got to be between 0 and 90. So cos theta must be equal to mg on t, and that can't be 0 because there's going to be tension in the string. We can calculate theta if we're given v and r, because we can get equation 2 that we had before divided by equation 1 and get tan theta is equal to v squared on rg. We always knew that tension was greater than mass times gravity, because if we look at this here cos theta is going to be going to be a fraction every time, so tension is going to be less than mass times gravity every time there. So tension can be calculated without knowing the inclination of the string as well, because we can have T sine theta is equal to mass times omega squared times R. So T sine theta would equal mass times omega squared, and we replace R with L sine theta, and the sine thetas cancel, so tension can be written as mass times omega squared times L. So we start to establish all these different situations. And the vertical depth will also be independent of the length of the string, because we can write T sine theta as mass times omega squared times R, and sine theta can be written on H on L, and this can be written that's equal to M times G, so T can be equal to L times M times G on H. But from 4 we know we had that situation, so M times L times omega squared equals L times M times G on H, and then we can do our cancellations of M and L, and then we get omega squared is equal to G on H, or H is equal to G times divided by the vertical the angular velocity squared, and that's independent of the length of the string. It's got nothing to do with it. And we can work out the period of revolution is equal to 2 pi times the square root of H on G from all that as well. So there's a number of situations that we can consider. So have a look at all those, and we will use those in a few problems that we're going to face in future videos.